The type of chemical reaction I want to talk about here is called a single displacement reaction. And a single displacement reaction is defined as a substance in elemental form, so an element, that replaces the cation in another substance. And it looks something kind of like this. So if I had a substance A that is considered an element, and I react that with another substance that has to, if it has a cation, must have an anion, so it's going to be considered a compound. And that compound had a cation B with an anion X. The definition of a single displacement is that substance in elemental form, the A, must take the place of B in the compound. So you would produce a new substance that is a compound that is AX and a new element that is only B. An example of this would be something like this. If I had aluminum that reacted with copper to bromide, what would happen is the aluminum would take the place of copper and combine with the anion bromide. Now keep in mind, bromide's anion is Br minus. The reason there is a 2 here in this substance is because copper, as copper 2, must take 2 bromides in order to form that compound as a neutral substance. So the subscript may not necessarily translate whenever you take that anion and combine it with the element aluminum. So, and this is true for, in this case, aluminum can only be +3. And so since aluminum is +3, it will need 3 bromine anions in order to balance to become a neutral compound. That would leave copper by itself as an elemental form. However, this isn't a balanced reaction. We should also balance reactions when we complete them. And we know that we need to put a 3 here to balance the bromines, a 2 here to balance, so there's 6 and 6 on each side. And then we can balance each element with their corresponding coefficient. So this final product here is a single displacement reaction that has been balanced. At this point, what I want you guys to do is I want you to be able to take a substance in elemental form and react that with a compound and replace the element in the place of the cation in the compound. The one thing that you must know in order to be able to do this is that this doesn't always happen. The reaction of replacing the element with the cation in the compound. It can only do so if the element wants the anion more than the already placed cation. And there's only really one way for you to be able to do this. To determine if this will actually happen is you must use this thing called an activity series. So an activity series, and this particular one is called a metal activity series, gives you a list of metals, which also includes hydrogen in this list, that gives you a list of what's considered more active than others. So the way that this list would work is this is the most active at the top, and then you go to the least active at the bottom. And the way that this works would be if the element, in our particular case, the previous reaction, aluminum, is higher on the list than the cation in the compound, which in our case was copper, it is higher on the list, then yes, it will replace copper. If that is not true, then the reaction will not proceed forward. For instance, what I mean by that is if I had copper and I wanted to react that with aluminum bromide to produce products, because copper is lower on the list than aluminum, this reaction would not actually proceed forward. So no products or no reaction would occur in this case. So given that information, I would like for you to try and determine from these next single displacement reactions what the products would be if the reaction proceeds forward. So keep in mind you're going to need a metal activity series to be able to do this. So we're going to add this in here for you to be able to see. So we're going to do the first reaction with zinc and sulfuric acid. So let's look at where the metal and the hydrogen are on the list. And it turns out zinc is right here, and hydrogen from the H2SO4 is below. So this is below zinc. So that means, will the reaction proceed forward? Yes, it will. So now it is your job to figure out what the combination would be. Now keep in mind that zinc should replace the cation in the compound, and that's hydrogen. So how do you know what oxidation number zinc is going to be? And this could be because zinc is one of the transition metals that only has one charge, but also in this really nice diagram, it turns out that we can actually tell you what the charge becomes. It's actually right here. So zinc 2+. So I know if I put zinc with sulfate, it's 2+, sulfate's 2-, so I need 1 and 1 of each. And then I put hydrogen by itself. Now, in this particular case, hydrogen is one of the few elements that are diatomic. And since it's diatomic, you must put a subscripted 2 with that. There's only a few of those. These are all of the elements that are considered diatomic. So if you ever get one of those put by itself, then note that they need to have a 2 subscript. So at this particular juncture, we're going to make sure that everything's balanced, and it looks like, yeah, everything kind of worked out that way. These are your products here, and that's your single displacement reaction. Okay, let's try another one. So this one's sodium plus hydrochloric acid. What will the products be in this single displacement reaction? Well, let's look at the list. Sodium is located right here, and hydrogen again down below that, so it's below. Will this reaction happen? Yes, it will. And so let's take sodium and replace the hydrogen. Sodium is a +1 charge. You know that from either the list here as Na+ or the fact that it's in group 1. You only need one of those to combine with chlorine minus, which is -1. So it's +1 - 1 gives you a 0 net of the compound, and this gives you hydrogen by itself, but make sure it's diatomic. Okay, so that is another single displacement. Let's try another one. In this particular case, we have aluminum reacting with magnesium chloride. Will you have a reaction proceed forward? Let's check it out. Aluminum is right here. Oh, and then magnesium, look at this, is above it. So aluminum to magnesium. Aluminum, therefore, would not have as much activity as magnesium. Magnesium wants to be with the anion more. So will this reaction happen? Absolutely not. Nope, it will not. So this what you would write here is no reaction. There are no products that form. All right, let's try one last one. This one is iron to react with tin to nitrate. So let's determine if this reaction will actually proceed forward, and if it will, we'll figure out what its products will be. So let's find iron on here. So iron is right here. Tin, Sn, is right here. Oh, it's below iron. So yes, this reaction will proceed. And let's look to make sure that we know what charge iron will become, and it's F2, Fe2 plus. So we'll do Fe, it's 2 plus. Nitrates are all -1. So we'll need 2 of those to combine with Fe2 plus, and then we'll have 10 by itself. Now in this case, 10 is not considered a diatomic molecule, so you don't put a subscript behind that. We should make sure that this is balanced, and it looks like it is, so we're good to go on that. These are your 2 products, iron 2 nitrate and tin. Okay, those are single displacement reactions. Keep in mind that you will need the addition of the metal activity series. You can write this series down from this lecture, or there is a copy of this in your text in OpenStax.